We're going to talk about complex ions. What is a complex ion? Well, what I've drawn here is we've got sodium ion in solution, and we know that the water molecules are going to surround it like that. You know, the water molecules have a dipole. You've got a partial positive charge, partial negative charge on the oxygen, and that's going to be attracted to the sodium ion. Now with transition metals, so let's think about transition metal ions. Let's think about copper, which we're very familiar with, and I would say the transition metals that you're probably really familiar with already are copper 2+, iron 2+, which is a pale green color, and probably iron 3+, which is usually a brown color. Okay, so what happens there is the water molecules don't just form a loose association. They actually, one of the lone pairs on the oxygens actually forms a dative covalent bond to the copper ion. So here, once again, we see metals forming covalent bonds. Of course, there's two lone pairs in each oxygen. Only one forms a. So you get water molecules surrounding it. Right now, these are dative bonds. So this would be the complex ion. Now, I've only drawn 4 water molecules. In reality, copper actually always has 6 water molecules around it, and most ions do actually have 6. But these 3 certainly do. So you'd write down, to show the 6, you write down copper H2O 6. And then you put the charge outside the bracket, because this charge now really is not just sitting on the copper; it's spread over the whole of the complex to some extent. It's not. It's just the whole complex has got 2 more protons than it's got electrons, so it's positively charged. Now, let's. These water molecules, these are called the ligands. Okay. These are ligands, and what the ligands do, they donate a pair of electrons to the metal ion and form a dative bond. So in the complex, the water molecules are actually covalently bonded to the copper. They're not just loosely associated. Right, let's think about how they're arranged. You've got 8 of them, and they are arranged, they get as far away from each other as possible in an octahedral fashion. So if I draw sort of flat plane like that, so you're going to have your copper in the middle, and you're going to have the water molecules here, dated bond, one there, one there. So the bond angles are all 90, and then you have one sticking down and one sticking up, and so they're all dated bonds. We just remind ourselves by putting the arrow on. And the shape of this complex is octahedral. Right, and most transition metals, they all have, as I said, they have 6 water molecules and they form octahedral complexes. So, you know, we've got Fe H2O 6 2+. I'm familiar with Fe H2O 6 of them with a 3+. And then some of the ones we're not familiar with, we'll come to later. For example, vanadium 2+, so H2O, 6 of those, 2+ charge there. So most transition metal ions form these octahedral complexes with water. We have 6 water molecules there. So, right, we've talked about water as a ligand. What other ligands could we have? So ligands, what do they need? They need to have a lone pair of electrons. Yeah. Quite often they are charged. They're negatively charged, so they'll be attracted to the positive metal ion. So let's think about some common ligands. Right, well, there's H2O. lone pair on the oxygen there. There's also ammonia. That is a good ligand. You've got a lone pair on the nitrogen, forms the dative bond. The cyanide ion. So you've got triple bond to the nitrogen, and then you've got, this is negatively charged, one electron from the carbon, one that it's stolen from somewhere else. The cyanide ion is a good ligand. That is why cyanide is poisonous, because it forms a complex with iron atoms in the cytochrome oxidase in the mitochondria, the enzymes of the mitochondria, and stops them working. It's a good ligand. And there will also another one we have to think about. It's not as good as them, but chloride ion, because it's a little bit too big, Cl minus. Okay, so you might have noticed that a lot of ligands, you could also, in organic chemistry, they'd probably be good nucleophiles, because they've got a lone pair of electrons on, they've got a lone pair which they can donate. They have a negative charge on them, or just a partial negative charge on the atom of the lone pair. Okay, so now ligands can swap places with each other in so-called ligand exchange reactions. So we're going to talk about a couple of them. Ligand exchange reactions. And there's two pretty important ones, and we are going to talk about ligand exchange reactions involving copper 2+, okay? Right, so if I get a test tube of copper sulfate, and that's kind of a palish blue color, like that. And then if I add some conch ammonia to it, what happens is the color changes and it goes a very dark blue, like a royal blue inky sort of color. And we'll talk about what's happened there. It's because the water ligands have been swapped, or some of the water ligands have been swapped for ammonia ligands. And when you change the ligand, you very often change the color of the ion. All right. Also, if we add some conch HCl to this. Now, conch HCl is it's got loads of chloride ions in it. If you do that, it turns into a really lovely emerald sort of color. And that's because you push some of the water molecules out and replace them with chloride ions. So there's two ligand exchange reactions, and I would definitely remember these ones. You don't have to know every single color of every single transition metal ion and every single ligand exchange reactions, but there's a few good illustrative examples like this one. It's a very good idea to know them. Right, let's just see what's happening there. So with the with this one, right, what happens is you get copper H2O 6 2+, and when you add ammonia to it, you push out some of the water molecules, and you end up with Cu H2O 2. You leave 2 behind, and 4 are replaced by ammonias. So the charge on it is still 2+. To balance that, I'm going to have to put a 4 there. And then on this side, I'm going to have the 4 water molecules that are replaced by the ammonias. And we'll see later that this complex is still octahedral, and you end up with the 4 ammonia ligands. They're all in the flat plane, and the 2 waters, one sticking up and one sticking down. Don't worry about that too much for the time being, but that is a good example of a ligand exchange reaction, and this one is still octahedral. Let's see what happens with this one. Is a little bit different. So we've got copper H2O6, and we'll give some chloride ions, and you get CuCl4. Now you can't replace, you can't get you can't get 6 chlorides ions around 1 copper because they're too big, and that's why you only get 4 in this complex. And also the charge on the copper would be 2 plus. Each of those is 1 minus. So the overall charge on that complex ion is 2 minus. And the shape of this is tetrahedral. So if you you've got your central copper ion there. You'd have one, they're in the same plane, but one coming towards you, one chloride, and one going away from you. So we should do dotted line for that one. Okay, so you get a tetrahedral complex, whereas we said this one up here, this one is still octahedral. I think one other ligand exchange reaction you should know about is cobalt. Right, it's very similar to copper. So cobalt 2 plus is a really nice pink color. So you get a test tube of cobalt 2 plus. Pink, we need a pale pink really. Okay, it will be, yeah, that is more or less the exact color it is. That's cobalt 2 plus. This is the hex aqua complex, so 6 waters. That's a nice pink color. And you add some conc HCl to that, and it will turn to a sort of pale blue color. You get a change in remember cobalt chloride paper, I think they use it in biology to test for water. Well, what it is you make some of this blue complex here, the chloride ions, and if you add water to it, it goes backwards and it goes pink. So that's like the little test for water. Okay, so conc HCl, and we write the equation there is the same as copper. You get cobalt H2O 6 2 plus. We add again, it's only 4 chloride ions can fit around it because they're too big. You get cobalt CO4 2 minus, and you'll get 6 waters coming off. Should put the 6 waters in there as well, and that's a tetrahedral complex. So you definitely need to know about those ligand exchange reactions. Before we finish up, I'm going to talk about one other peculiarity, really, which is the silver ion. Unusually, that doesn't have 6 water ligands; it only has 2. So Ag H2O 2. I have no idea why that is, but it does. It's just a 1 plus. And if you want to know the shape of that, well, they'd try and get as far away from each other as possible. So here would be your water molecules. And the shape of that is linear, and the bond angle would be 180 degrees. So silver is a bit of a peculiarity. And a good example of a ligand exchange with silver is we've done it when you make Tollens tests, because you remember Tollens is usually described as ammoniacal silver nitrate. And to make Tollens tests, you start off with Ag H2O 2, and you add some dilute ammonia to it. So you add NH3. You're going to need 2 of those because you're going to have to kick both waters out, and you end up with NH3 2, and you've got a positive charge. And this is the species that you've got present in Tollens reagent. Okay, again, right. So one last thing before we finish off, we've got to just define what this term coordination number is. Coordination number is the number of dative bonds formed to the central ion. So the coordination number in this one would be 2. Yeah. In this one, it would be 6, and in the tetrahedral complex here, the coordination number would be 4. Okay, we'll leave it there.